we will derive the Euler-Lagrange equation. Euler-Lagrange equation. The way we derive the Euler-Lagrange equation, it's a part of calculus of variation. Calculus of variation. And the main idea of calculus of variation is that in calculus of variation we use extremum of certain quantities. So the typical type of problem that you will get in calculus of variation is something like this. Now, let's say we are in the xy plane and there are 2 points in this plane, x1, y1 and x2, y2. Okay. Here x is the independent variable, x is the independent variable, and y is some function of x. And our goal is to find out what is the function of x that connects these 2 points. Okay. Now there are several such functions that are possible which can connect these 2 points, x1, y1 and x2, y2. So there is a constraint, and essentially the idea of calculus of variation is to use this constraint to find the functional form of y of x. So this is how we will do it. Let's say that there is a function f which is a function of y, x, y and y prime, where y prime is simply dy by dx. Okay, so there is a function, and that function depends on x, the independent variable, y, the dependent variable, and y prime, which is the derivative of y with respect to x. And then there is a integral j. This integral is defined from 1 to 2, point 1 to point 2, along the curve y of x. Okay, and this integral is f of x, y, y prime dx. So we can calculate this integral, which is simply the integral of this function x, y, y prime dx from point 1 to point 2 along some curve. And this curve, the integral is defined in such a manner that if you integrate this function, or if you calculate this integral over the curve y of x, then this integral j of x, y, y prime is an extremum. So extremum might mean it's either a maximum or a minimum. So this is the constraint that we were talking about. What we have is we have a function y of x which is defined from 2 points 1 and 2. We know the value of y of x at these 2 points, which is x1, y1 and x2, y2, and we want to find what would be the function y of x such that the integral j, which is defined as f of x, y, y prime dx, would be an extremum. So y of x, this integral essentially provides the constraint that defines y of x completely. Okay, so how do we do this? To do this, we use a very simple trick. So we know that j is an extremum along the curve y of x. So if we move a little bit away, infinitesimally away from y of x, then we expect that if we take the derivative, then we expect that since j of x, y, y prime is an extremum along y of x, if you make an infinitesimal change, that would not change the value of j. Okay, that is the definition of being an extremum, a maximum or a minimum. And in terms of calculus, what that means is that if you take the derivative of j along some path which is infinitesimally close to y of x, then the first derivative of j must be equal to 0. That's the idea that we are going to use. So let's see how we do it. So to do this, what we will do is we'll first define a new function y of x alpha. Now y of x alpha is defined as y of x plus alpha times eta of x. Okay, so if alpha was equal to 0, then this term would equal to 0. So y of x0 would simply be y of x. What that means is that if alpha is equal to 0, then this new path that we have defined is the same as the path that we are looking for, or y of x. When alpha is not equal to 0, then there is a difference. So when alpha is not equal to 0, then we have y of x alpha minus y of x equals alpha times eta x. So eta x essentially defines what is the difference between the new function that we have defined and the function that we are looking for, okay, up to a constant alpha. So eta x essentially is the change. So if this curve was y of x, then eta x, which I'm going to draw here in green, is a line or a curve very close to or this green line is actually y of x alpha, and the difference between them is eta x. Okay, so now that we know what is y of x alpha, there's another important point to note about eta x is that eta x is defined in such a manner that eta of x1 and eta of x2, they are all equal to 0. Okay, so eta of x1 equals 0 and eta of x2 equal to 0. What does that mean? That means that if you go to the point 1 or point 2, then at those 2 points, y of x alpha and y of x, they are similar. So they don't differ at the beginning point and at the end point. At every other point they can change, but the beginning and the end is defined, and that's why eta of x1 and eta of x2 is equal to 0. Okay, now that we have made all these things, let's do one more. Let's do just one more thing which will be useful later. So this will be useful later, this will be useful later, and we will do one more. Let's look at this quantity del y or dy by d alpha. We can look at this quantity dy by d alpha. So dy by d alpha is simply going to be, alpha appears only here, it's going to be eta of x. Okay, so dy by d alpha is eta of x, and since dy by d alpha is equal to eta of x, dy by d alpha at the point x1 and at the point x2, these are simply going to be eta 1x or eta 2x, which is also going to be equal to 0. Okay, so we are going to use these things later on in our derivation. Now that we have defined this function y of x alpha, we can write j of x, y, y prime. So j of x, y, y prime, remember, was defined as f of x, y, y prime dx. And we were doing this integral along the path y of x from point 1 to 2. But we can also define this j along the new path that we have created. So we can write x y of x alpha, y prime of x alpha. This would be equal to integral along y of x alpha, f of x, y of x alpha, y prime of x alpha dx. So this integral is now along the new path that we have defined, which is y of x alpha. Why are we doing this? Because the reason we are doing this is once we have j as a function of x and alpha, we can look at the quantity dj by d alpha. Okay, dj by d alpha, since this path is infinitesimally close, that's how we have defined. If we look at the quantity dj by d alpha, that must be equal to 0 at alpha equals 0. Because when alpha is equal to 0, then we could go back to the original function y of x. So if we are interested in, since we are looking for y of x, which is along which this function j is an extremum, if we look at the derivative of j with respect to alpha, and alpha is very, very small or approaching 0, then this quantity must be equal to 0. So what we need to do now is we need to find out what is the derivative of j with respect to alpha. That's what we will do next. So we are interested in dj over d alpha. dj over d alpha would be d by d alpha of the integral f of x, y, which is a function of x and alpha, and y prime, which is a function of x and alpha, dx. What we can do is we can take this, and this goes from x1 to x2. We can take the differentiation inside the integral sign, which will give us x1 to x2 d by d alpha of the function f x, y, x alpha, y prime of x alpha dx. And now we will just do the derivative of this function. So this would be x1 to x2. Now f is a function of x, y, and y prime. So what we will have to do is we'll have to do the derivative of each one of these terms. And if you don't know how to do this, you should look at what is the chain rule. According to the chain rule, this should be written as del f by del x into dx by d alpha plus del f by del y into dy by d alpha plus del f by del y prime into dy prime by d alpha dx. Okay, this is a simple using of there are multiple variables. We just use the chain rule to write it this way. Now we know that x is an independent variable. It doesn't depend on alpha. So this quantity must be equal to 0. So now this integral can be written as x1 to x2 partial derivative of f by partial derivative of y dy by d alpha plus partial derivative of f by partial derivative of y prime dy prime by d alpha dx. Okay, now you see here that these quantities, here the derivative is with respect to alpha, dy by d alpha. Here we have dy prime by d alpha. So what we are going to do next is we are going to just work with the second term, this term, such that we convert this dy prime by d alpha into something that looks like dy by d alpha. And then once we do that, we'll be able to take out this other part or take that part out as common. So that's what our next step is. So how do we do that? It's very simple. What we do is we use integration by parts. So let's do integral x1 to x2. The first term is simply del f by del y by dy by d alpha. And the second term, if you remember that y prime is simply dy by dx, right? Y prime was defined as dy by dx. So this second term can be written as d by dx, or d by d alpha of d by dx. Okay? So the second term is d by d alpha of dy by dx. And then we have this integral dx. Now what we are going to do is, for the second term, we are going to do integral by parts. So here we have two terms. One is d partial derivative of f with respect to partial derivative of y prime. And the second term is the partial derivative of the full derivative, the full derivative of dy by dx with respect to alpha. So we will use integral by parts. If you do not remember integral by parts, the formula is simple. Let's say you have two functions g and h that you are integrating with respect to x. The integration by parts says that the integral of gh dx should be g, the integral of h dx, minus the integral of the derivative of g integral of h dx, and the whole thing integrated. Okay, so this is the formula for integration by parts. So what we will do here is we'll take del f by del y as our first function g and the second function as h. So let's do that, and let's calculate the integral. So the first term remains again very similar, x1 to x2 del f by del y dy by d alpha. The second term, what we can do is, the second term we can write using the formula here, del f by del y prime integral of x1 to x2 d by d alpha of dy by dx minus the integral x1 to x2, the full derivative of del f by del y prime, integral of d by d alpha dy by dx into dx, and then the whole thing integrated. Okay? This is okay. So the next step is, for the next step, what we do is we take x1 to x2 partial derivative of f, partial derivative of y, dy by d alpha, plus del f by del y prime integral of x1 to x2. You see, we have d by d alpha of dy by dx integrated over dx. Now, what we can do here, because these are full derivatives, we can change the order of differentiation, and we can write it as d by dx of dy by d alpha into dx. And we can do the same thing in the other term. So we have x1 to x2 dy by dx del f by del y prime, and then we have the integral d by dx of dy by d alpha dx, and then the whole thing integrated. Okay, so now if you look at this term, we have d by dx of some function, and we are integrating over dx, which simply means that the integral will give me dy, whatever that function is. So here, now the first term becomes x1 to x2 del f by del y dy by d alpha. For the second term, we can write partial derivative of f with respect to partial derivative of y prime. And after integrating, we will simply get dy by d alpha, calculated at the point x1 and x2. For the second part, we will get x1 to x2 d by dx of del f by del y prime. And again, it's the same integral, so it will give me dy by d alpha, and then we will have a dx coming from the term here. Okay. So now we are almost done. Now remember that the partial derivative of y with respect to alpha was eta of x, right? The partial derivative of y, the full derivative of y with respect to alpha was eta of x, and eta of x at the point x1 and x2 are 0. So this derivative of y with respect to alpha at x1 and x2 is going to be equal to 0. And that's why this term is equal to 0. Okay. Now you can also see that I should have a dx in all these terms. Now you can also see that in the first term here and this last term here, both these terms have a dy by d alpha dx. This is the reason we did this part integration by parts. So now both these terms are being integrated from x1 to x2. They have some function, and apart from that function, we have dy by d alpha dx in both these quantities. So what we are going to do is we are going to write, we are going to take the common parts together and write this as integral from x1 to x2. Both of them are being integrated over the same range, and we can under bracket we will write del f by del y minus d by dx of del f by del y prime. These are the two terms. This is the first term is from here, del f by del y. The second is this part, d by dx of del f by del y prime, and everything else is the term which are common in both these terms, the first term and the second term. Okay, and now remember, so what we have done is we have written j del j by del alpha becomes integral of x1 to x2 partial derivative of f with respect to y minus d by dx of partial derivative of f with respect to y prime dy by d alpha dx. But the constraint that we had said that the partial derivative of j with respect to alpha must be equal to 0 for alpha equal to 0. That's because j is supposed to be an extremum. So the quantity del j by del alpha at alpha equal to 0 must be equal to 0, which means that this integral must be equal to 0. Now, if this integral is equal to 0, let me erase this part. If this integral is equal to 0, it means that either the part which is inside the integral has to be equal to 0, because dx, x is an independent quantity, so we can choose it to be such that dx is not equal to 0. Also, dy by d alpha, remember we have constructed the function y of x alpha. So we can construct it in such a way that dy by d alpha is not equal to 0. So since we can construct it in this specific way, that this is not equal to 0 and this is not equal to 0, the only possibility which remains is that this quantity, which is del f by del y minus d by dx of the partial derivative of f by partial derivative of y prime, this must be equal to 0. Okay, and this is our Euler-Lagrange equation. Euler-Lagrange equation. Okay, what this equation does, it gives us a differential equation for y. So this equation typically gives us the differential equation for y, and once we have that differential equation, we can solve that differential equation to find the function y of x. Okay, we will see how to use this formulation in our examples, which you can watch in the next video. Thank you.